the 5th lecture of this series. I remind you that we are talking about the science of light and how the knowledge and the discoveries made about light over the centuries have led to the modern science, modern revolution in science. During the last 2 lectures, I discussed what happened at the beginning of the 20th century, the discoveries which have followed what Lord Kelvin called the 2 clouds which were obscuring the sky of physics. One cloud was the impossibility to explain the spectrum of thermal radiation, and this led to the quantum revolution. And the other cloud was related to the problem of the speed of light, and this led to relativity. So last week I discussed the beginning of quantum physics. I explained how the discoveries that the exchange of energy between matter and light were made by quanta, by jumps, which were interpreted by Einstein as the fact that light was made of particles, which were later called photons. And we saw that this introduction of quanta in physics, which started with light, then was generalized to other fields. The quanta were also important to understand the heat capacity of solids, for instance, by Einstein again. And then Einstein came back to Planck's law and found that it was possible to explain it by making the balance between the exchange of absorption and emission of light by matter, and he discovered stimulated emission, which 40 or 50 years later resulted in the invention of the laser. And also another big advance which happened at that time was the fact that it was discovered that the photons obeyed to statistics which was different from the classical statistics used by Boltzmann. And this led again Einstein to discover the properties of special kind of atoms which obey to the same statistics as the photons. And we discussed this, the Bose-Einstein condensation. So all these events which happened between 1900 and 1924 made a kind of rather disparate set of phenomena which lacked a common explanation. The situation was a little bit the same as the one which occurred in the mid of the 19th century, when electricity, magnetism, and optics had been studied, but are still lacking a common explanation for this phenomena. And so this happened around 1925, and this will be the discussion I would like to make today. So in today's lecture, I will discuss the emergence of the theoretical framework of quantum theory and its physical interpretation. And it will be, I will be discussing the physics which occurred between 1925 and or the 1925 and 1930. The first event will be the introduction, of course, of matter waves by de Broglie. And I will discuss this point, which was really the turning point of the advent of modern quantum physics. Then I will talk about the discovery of Schrödinger's equation, which describes the evolution of matter waves. And the Schrödinger equation plays a little bit the role of Maxwell's equation. It's an equation which gives quantitatively the way to explain and to describe a lot of phenomena occurring in physics and in chemistry, for instance. I will talk also about the Heisenberg uncertainty relations and the Bohr complementarity principle. I will explain how these ideas have been tested again by thought experiments, in particular by Einstein and Bohr. And I will talk about the consequences of the Heisenberg uncertainty relation for the stability of atoms. And I will talk also about the relationship between the phase and the amplitude of an oscillator, which are effects which will be important in the following of the lecture. So this will be the first part. And after the break, I will make a brief description of the modern quantum theory using the mathematical formalism which was introduced by Dirac around in the 1930s. This formalism describes the quantum state of a system you represent them as a vector which evolved in an abstract space. It looks a little bit like the usual vector space of ordinary space of ordinary world surrounding us, but these vectors belong to a different space because they can be affected by complex number coefficients, which would play the role of probability amplitude. So I will discuss that in the second part of the lecture. I will talk about the physical observable, how you describe quantities that you measure in an experiment. I will tell you that these observables are represented by operators which act in the Hilbert space. And the eigenvalues of these observables are the possible result of a measurement. So I will recall the measurement postulates of quantum physics, and I will try to relate this more formal approach to the semi-qualitative description of complementarity in Heisenberg and uncertainty relations, which have preceded this formal description. And I will try to make sense of all this and to give the broad ideas about quantum phenomena, and especially discuss why and how it is very different from classical physics. So if we want to talk about, follow the history, we are now in 1924, just a few weeks after Einstein received the letter by Bose and started being interested in the Bose-Einstein condensation phenomena. He received a letter from Paul Langevin. Langevin had a student, Louis de Broglie, who had, in his thesis, made the very bold hypothesis that matter was also made of waves. The same kind of particle wave dualism which had been produced for photons by Einstein should extend to material particles as well. And Langevin did not know what to think about that. So he asked to Einstein his advice. Einstein read the thesis and found it very interesting. And so he wrote back to Langevin the sentence I have written here, which has become very famous. De Broglie's thesis has lifted the corner of the great veil to try to make sense of all these disparate phenomena I was talking to you about. And he wrote to Lorentz also. The young de Broglie has made a very interesting attempt to interpret the Bohr-Sommerfeld quantization rules. These are the rules which explain the spectra of hydrogen. I think it is the first ray of weak light to eliminate these rules, the worst of our physical puzzles. And I have also discovered something which supports this construction. And what he refers to is that he saw the connection between the Broglie ID and the Bose-Einstein condensation, as we will see in a moment. So, but I think what is important is that de Broglie made his discovery by analyzing the papers of Einstein of 1905, the paper on the photon and the paper on relativity. And he was influenced by these two papers. And of course, it resonated with Einstein because Einstein understood that de Broglie has been digging further into these phenomena to understand what the quantum world was about. So what did de Broglie discover? He made a comparison between what happens with the photon and a material particle. You see, the photon, a photon has a wavelength which is c over the frequency nu, and if you write h nu over c here, you find that you can write lambda is h over p, where p is the momentum of the photon. And so the idea of de Broglie was very simple. Why we don't extend this formula also to matter? And you write that the wavelength associated to matter particle is h over p. P is equal to mv. So you get this famous formula h over mv, which shows that the wavelength should become larger and larger when the velocity of the particle decreases, and of course when the mass decreases. So what happens in usual physics at large wavelengths is at large velocities, lambda is so small that there is no physical effects observable. You have to be at very low temperature, so the velocity is very small to get large lambdas. And this again is something that had been understood before, the fact that quantum effects occur at low temperatures, basically. But it was rather strange because Du Bois used the photon, which is a relativistic particle, which goes at the speed of light and has zero mass, to extend this to describe classical non-relativistic physics. When you use the formula P equal mv, you assume that you are with low velocities which are small, and of course it's non-relativistic. So it was a kind of mixture between relativity and classical physics. And moreover, there is a connection, another connection with relativity. I remind you that the phase, according to, if you write the wave function, the function of this wave as having a wavelength lambda, you have a dependence over space, which is of the form minus 2i pi x over lambda, which you can write ei px over h bar. And I remind you that the quantity px is something which appears in relativity as one part of a quadratic vector, px minus et, is a quantity which is conserved for a free particle in relativity, which describes the action of the particle. So if you assume that the spatial part of psi takes this form, you have to complete it with the time part of the same quantity, and you get psi of RC is equal to EI px minus ET over h bar. So quite naturally, you come to this formula that a free particle is like a plane wave, which has a momentum p and an energy E, and a phase which evolves according to this expression. E is the energy of the free particle, and this energy, of course, we know is equal to p squared over 2m in non-relativistic physics, when the velocity of the particle is small compared to the velocity of light. So then what Du Bois did is to use this semi-qualitative picture to try to explain the Bohr quantization rule. I remind you that Bohr quantized the angular momentum mvr, and he just wrote that the angular momentum on a circular orbit should be an integer number of h bar. But you see immediately that if this formula can be written as 2 pi r is equal to n lambda de Broglie, because lambda de Broglie is given by this. So you see immediately that the quantization rule of Bohr just means that you have an integer number of wavelengths around the circle. So this quantization just means that you should, that the Du Bois wave, which is running around the nucleus, should close itself after an integer number of wavelengths. This is a resonance condition. It's like the condition of resonance of a string between two endpoints, except that this is just a circular quantization condition. But he retrieved in this way the Bohr quantization rule in a way which is less arbitrary to what Bohr said. So this quantization was a great success of this hypothesis. The principal number of Bohr theory is just the number of Du Bois wavelengths which are accommodated along the orbit. In fact, Bohr assumed that the angular momentum is n h bar. We will see the Schrödinger equation shows that in fact this electron angular momentum is n minus 1 and not n. But if you take n large, the difference is small, and Bohr made all his calculation by assuming that he was at the meet of large quantum numbers to make the connection between quantum and classical physics. So this was one point. Another point which immediately struck Einstein is that the connection with the Bose-Einstein condensation. I remind you that Einstein found the condition for Bose-Einstein condensation by calculating the maximum density of atoms which can be sustained in a gas before the gas collapses and before the atoms have to go into the condensed phase. And for that, he had to calculate the number of available states. And this number was obtained by assuming that the phase space of the atom was divided into elementary cells of volume h cubed, where h is Planck's constant. And the calculation yielded the formula that you see on the blackboard. And Einstein immediately recognized that the term under bracket is just the cube of the inverse of the cube of a quantity which is a double wavelength, h squared over 2 pi m k Boltzmann t. If you take the square root of that, you get something which is of the form h over mv, where v is the thermal velocity of the gas at temperature T within a constant, which is not relevant here. So what Einstein understood immediately is that what happens when you cool the gas, that the double wavelength increases. And at some point, the double wavelength becomes of the order of the separation between the atoms. And at that time, everything condensates. So it's a clear physical interpretation. You start to see quantum effects when the double wavelength becomes comparable with another relevant quantity, which is the average distance between the atoms. So it's a little bit like the connection between ray optics and wave optics. You know that the light is going in straight direction as long as the wavelength is small compared to the size of the obstacles. Here, the materials behave classically as long as the double wavelength of the atoms is small compared to the distance between the atoms. So that made sense. And it was something which made Einstein feel that the Broglie was on the right track. Then, of course, the next question was, it was very qualitative. If you have a wave, what is the wave equation? There was something which was lacking. It's like for Maxwell's equation, for the theory of light, it was not sufficient to say that light was a wave. It was important to have the Maxwell's equation, which described how the light propagates. And here also, there was a need to find the propagation equation. In fact, this was a question which was asked to Schrödinger. Schrödinger was working in Zurich, and in a seminar, he explained the Broglie's work. And one person who attended the seminar asked Schrödinger, but where is the equation for this wave? And so this triggered a very intense work by Schrödinger. It took him several months, and he came up with what is now known as Schrödinger's equation. So I try to give you just an intuitive derivation of this equation. If you assume that psi is equal to EIPR minus ET, if you take the second derivative with respect to space, you get P squared times psi. And if you take the first derivative with respect to time, you get E. And so if you equate E to P squared, you will have to equate the first derivative in time with a second derivative in space. And this is what the equation is about. You get this equation, the derivation psi over time, which gives the energy E, has to be equal, because of the sign here, minus h squared over 2m times the sum of the second derivative with respect to space, which is the Laplacian. So you get this equation, which is just the propagation equation of the Schrödinger wave for a free particle. The next point is, of course, if you want to understand the hydrogen atom, you have to add to this free equation the contribution of the potential. And so the simplest thing to do is to add, just to add to the kinetic, to this term which represents the kinetic energy, a term which is U times psi, which represents the potential energy. And this is Schrödinger's equation for a particle in an electric, for example, for a charged particle in an electric field. So this is the equation that Schrödinger came to. What I want to say is that this, of course, this is not a derivation. This is something which is a little bit heuristic. In fact, what Schrödinger did was something much more formal. He started from the Lagrangian and Hamiltonian point of view of mechanics and made a correspondence which led him to this equation. But I don't want to discuss this aspect. We have to assume, we have to consider that Schrödinger's equation is a kind of principle, and it is justified by all the consequences. If you use this equation, you find the hydrogen spectrum. If you use the same equation extended to many particles, and I will come to that in a moment, you cannot solve it exactly. You have to solve it using the approximation methods. but then you find the spectra of all atoms, you find the spectra of molecules, you understand condensed matter, the behavior of electrons in matter. So the success of this equation, which explains all of microscopic physics and chemistry, is the real justification of the validity of this equation. So I will just write this equation. If you have not one but n particles, you write exactly the same equation, just add all the kinetic energies, the sum over the particles which are labeled by an index I, and you have the potential which depends upon the position of all the particles. For example, the electrostatic potential between the particles and the nuclei. And you get this equation, which is the equation which is used in chemistry and in physics to describe the spectra of atoms and molecules. And of course, you have to use approximations. But the fact that you use approximation to solve the equation has been known for a very long time. If you take astronomy, as soon as you have more than one planet, you cannot solve exactly the problem, and you use approximations. And these approximations are very, very good and give you a very good quantitative explanation for all the phenomena. An important point here, which I will come back to in this talk, is that this equation is linear in psi. It means that if you have two solutions, psi1 and psi2, any linear combination of this solution will be the solution. And this is something which looks a little bit like Maxwell's equation. You can combine solutions, so you will have interference effects. These waves will be able to interfere as electromagnetic waves. The last point I would like to make here before going to another issue is that this is a non-relativistic equation. It's obviously non-relativistic because it does not deal with space and time on an equal footing. It takes, you have second derivative in space and first derivative in time. So it's not a relativistic equation. And 3 years later, in 1928, Dirac discovered an equation which is at the same order in space and time, and which is known as Dirac equation, and I will talk about it a little bit next week. So this equation is, I remind you again, the equation here. The problem which was raised at that time, and Schrödinger did not have at the beginning a clear solution about this. It's a wave, but a wave of what? The light is a wave of electric and magnetic field. An acoustic wave is a wave compression of air. So you need a medium for the propagation of air, of sound wave in air. You don't need a medium because the ether has disappeared for relativity. So what kind of, do you need a medium for these waves? What does that mean? And the solution was given by Max Born very soon, I think in 25 or 26. He said this is a wave of probability. It's a mathematical wave whose square, and in fact the square of the modulus, represents the probability to measure the particle or to measure the configuration of particles in a different set of points. So this is what I have written here. Psi squared at R1, R2, and so on, times the elementary volumes gives the probability to the joint probability to find the particles in small volume elements around the different positions. So, and this was a very big point and something that Einstein did not like at all, because this means that the theory is probabilistic. Up to now in physics, determinism was considered to be absolutely essential and was a dogma. That is, if you know the initial conditions, you know exactly what you will measure later. In quantum physics, you can only compute the probability of events. And this is, you have to renounce the determinism of classical physics. And this is a very big point here. The wave function allows you to compute probabilities with a very high precision, but these are not, chance becomes a very important parameter. So this evolution equation is deterministic as long as you don't make any measurement. It tells you how the wave function evolves, how the probabilities to get results if you do an experiment will evolve, but as soon as you make a measurement, you have something undeterministic which happens. And we'll come back to this in a moment. So I've tried in the next slide to describe this on a simple example. Assume that you have in one dimension a wave function which has this shape, showing some interference effects, as you can see here. And you decide to measure X. You make a measurement. And after the measurement, you find, of course, if you make a measurement, you will find one value for X. But what happens is that the wave function immediately collapses. And instead of having all the possibilities for X, you just get the values that you have obtained. And this is something which is irreversible. So, in fact, as Einstein said, in quantum physics, God is playing dice. You have always kind of casting a dice, looking at the probabilities and deciding that one event occurs according to the probability law. It means that if you resume the same experiment with the same initial system, you will find something else, and the histogram of all the results will give you the probability distribution. And that's something that Einstein did not like at all. So Einstein, during all the rest of his life, fought against that. He understood that very well. He understood that these rules allowed to make very clear calculation, very precise calculation, but he thought that there was something missing and that the real theory should avoid this kind of undeterminism in quantum physics. I will now want to discuss a very important issue, which is Heisenberg uncertainty relations. So on this slide, I remind you about what happens if you take a wave packet of light. Assume that you have a light pulse, which I have written here. And you see this light pulse is a superposition of plane waves of different frequencies omega and wave vector k, where k is just equal to omega over c. So if you make a packet of these waves, you have a pulse of light which propagates at the speed of light. And what happens, what does this dispersion in omega and k value mean? It means that, for instance, if you, I will first consider the variation with z. I will assume that I am at time t equals 0, and I want to know what is the shape of the wave packet if I change the position. It's clear that then you have to consider the EIKZ term and sum this over different values of k. And it's clear that if you depart from z equals 0, the phases kz will start to spread out. And when delta z will be of the order of delta k being the width of the packet, then you will have a negative interference and the wave will decay. So you see from this kind of argument that the spatial dimension of the wave packet is of the order of such that delta k delta z is equal to 1. So the larger delta k, the shorter is the wave packet in space. And you can make the same argument for time. If you just stay at a given point and look at what happens as time evolves, the waves with different omegas will spread out. And as soon as delta omega delta t will be of the order of 1, the wave packet will decay. So you have a spreading in space, which is 1 over delta k, and a spreading in time, which is 1 over delta omega. And this is just a mathematical consequence of what is known in mathematics as a Fourier transform. You see that, in fact, the variation as a function of time, f dt, which I've written here, is a Fourier transform of the distribution in momentum, in wave vector k. And you have this correspondence. The wider is a function in space, the narrower it is in k, and the same for the distribution in time. So this is a mathematical property, but which would have very important consequences. And in fact, this was discovered by a mathematician living in the beginning of the 19th century, Fourier. And Fourier was a colleague of Fresnel. And in fact, when Fresnel developed his model for the light, he used the Fourier series and he was working in collaboration with Fourier. So it was applied to light, but this also is important, as we see now in quantum physics. You can do exactly the same. You can make now a wave packet with de Broglie waves. Instead of summing waves which have a dispersion in k values, you sum waves which have a dispersion in p values. And you have the same problem. The difference, of course, there is a big difference with light waves. That is a dispersion. The connection between omega and k is linear, because omega is equal to ck. But the relation between the energy and the momentum is not linear, E is proportional to p squared. This means the difference means that if you take a wave packet of matter waves, when it propagates, it will change shape. It will spread out because of this nonlinear relationship. But the connection between the spatial and the momentum distribution is the same as for light. The delta X, delta K product, which is of the order of 1, becomes delta X, delta P of the order of h bar in quantum physics. So what does it mean? It means that if you localize a particle, if a particle is created at one point or if it's measured at one point, if it's well localized in position, it means that it has a distribution over many p values. And it means that it will very fast broaden because different p values means different velocities. And the precision with which you can determine the position and the momentum are related by this relation. And these are known as the Heisenberg uncertainty relations. You cannot measure at the same time, you cannot measure with an arbitrary precision, position and momentum. We will see in a moment that these quantities are said to be conjugated, then they correspond to observable, which cannot be measured simultaneously. And this relation is a very fundamental relation of quantum physics. In fact, I gave you here the derivation by Schrödinger, but in the year 1925, Heisenberg found another, independently from Schrödinger, another description of quantum physics, which was starting point was the fact that X and P were given by matrices which do not commute and which cannot be measured simultaneously with precision. And it was found later that the Schrödinger and Heisenberg point of view were completely equivalent. It was like the same physics translated into different languages, but with the same consequences. So this is a very important relation. And so I have summarized at the bottom the classical mathematics property, which take a deep quantum meaning. The better a particle is localized in space, the less well known its momentum, hence its velocity, and the opposite is true. The better the velocity is defined, the more diffuse is the position. So with this in mind, we can now analyze very simple experiments which Einstein and Bohr discussed in terms of thought experiments. You see, there is a very puzzling thing which is happening. Light was considered until the 20th century as made of waves, and the fundamental experiment was Young double slit experiment, which you can explain with wave. But now, if you have to consider it's also a particle, how do you explain the interference in this term? And if you consider now that particles are also waves, you have a very deep problem. So I remind you, what is the Young double slit experiment? You have a plane wave which arrives on a screen which has two holes in it, and so the light escaping from the wave escaping from the two holes interfere, and you have bright fringes when the difference of passes is a multiple of wavelengths, and you have dark fringes when the difference between the two passes is an odd number of half integrals. So this is quite clear if you have waves. And so what you have to consider is that these are probability waves, they interfere, and so the particle will be found where this interference is positive. So if you have a big number of particles, this is something which is quite clear. But now what happens, and this was the question that Einstein and Bohr asked themselves, what happens if the particles cross the system one at a time? If you have such a faint source that you have only one photon at a time, or one electron or one atom at a time, will you see interferences? And if you see them, what does it mean? At the time of Einstein and Bohr, these were thought experiments, but now they are being done in the lab, and I will show you the result on the next slides before trying to discuss that. So you see here, for instance, the interference of light beams when the source sends single photon at a time. It's done with a Fresnel biprism. I showed you the experimental setup in the second lecture. So it's like young double slit, and you see what happens. At the beginning, the first particles arrive, you have the feeling that you have kind of random points on the screen. And then when enough particles have arrived, they reconstruct a figure of interference. This has been done with photons. It has been done also about 20 years ago with electrons. And in fact, this is something that De Broglie had predicted. De Broglie said if we have matter waves, they should interfere. And indeed, they interfere. So the electrons interfere too. And it's exactly the same. The first electrons arrive randomly, apparently randomly. But when they constitute enough, there are enough particles to make an image of fringes, you see clearly fringes. So this is really puzzling, and it raises many questions that Bohr and Einstein discussed. When the experiment is performed with one particle at a time, it's really puzzling for physicists which used to think in terms of trajectories. For instance, if each particle passes through one hole or the other, how come that they never come on a dark fringe? How can, so this is what I have written here, how can the subsequent history of the particle depend on whether the other slit was open or closed? If you assume that the particle passes at the left slit, if the right slit is closed, it can go anywhere. If the right slit is open, it can go only in a bright fringe. So there is something very difficult to understand for a classical physicist. Another way to ask the question is, how can the particle know what is the state of the other slit to decide whether or not it can arrive on a dark fringe? So that's a really puzzling question if you assume that there is a trajectory for the particles in the apparatus. Another question is, what happens if we decide, without blocking the slit, to observe through which one did the particle pass? So can you change a little bit the setup and look at what happens at the position where you have the two slits and see through which slit they pass and what happens next? And this is what Einstein tried to do. And this is the kind of drawings they made to discuss their thought experiments. What the idea of Einstein was very simple. He said, I will just modify the setup a little bit. The upper slit will be on a kind of moving apparatus, moving device. It will be suspended by springs. And you see what will happen if the particle goes through the upper slit, it will be diffracted on the edge of the slit. The slit will start to move. And if the slit moves, we know that the particle passed through this slit. And if the particle goes through the lower slit, the upper slit will not move. So we will know where the particle, through which slit the particle is going, and will we see fringes? And so Bohr was immediately answered using the Heisenberg uncertainty relation. Bohr said, okay, what you are doing here is a different experiment. You have changed the setup, and so you have to be very careful. And if you want to see, if you want to know through which slit the particle went, it means that the momentum of this slit should be very well defined, because it will change a little bit, and if its momentum is fuzzy, the change will be unnoticeable. So you should have a very small delta p. But wait, if you have a very small delta p, delta x will be large. And if delta x is large, it means that the fringes will be blurred, because the separation between the interfringe spacing depends upon the separation between the two slits. And I don't do the calculation, I let you do it, but you see immediately that as soon as delta p is small enough so that you know through which slit the particle went, delta x becomes large enough so that you lose the fringes. And so Bohr said, you cannot talk about the trajectory of the particle without describing clearly what kind of experiment you are doing. And if you describe your experiment, you will find that the Heisenberg relation will prevent you to, at the same time, follow a trajectory and see interferences. And he said that, he stated that by what he calls the complementarity principle. He said that measuring the position of the particle or looking at fringes are two complementary experiments which cannot be performed at the same time. You have to choose if you do one or the other. And this is something which Bohr was adamant about. And what he said is that if fringes are observed, the trajectory has no physical reality. It does not mean anything to talk about a trajectory. In fact, the particle crosses the screen in a superposition state, going through two slits at the same time. In fact, more precisely, it's a probability wave which passes through the two slits at the same time, but it has no meaning to talk about the trajectory. If you want to talk about the trajectory, do an experiment. If you see the trajectory, you will not see the fringes. And this is what the formalism of quantum physics I will be talking about in a moment explains. So the complementarity ideas of Bohr are very qualitative, but it's contained in the theory, as we will see in a moment. So, and this discussion occurred during another Solvay meeting. It was a Solvay meeting of 1927, 16 years after the one I showed you last week. And I don't know, you see clearly now Einstein has gained a lot of status. So you see he was sitting in front near Lorentz. Lorentz was very old, it was 1 year before his death. So you see on the first row Einstein, Lorentz, here you see Langevin. And in the back, you have the young people, Heisenberg, de Broglie, Dirac, Bohr, were junior people, and they were not given a seat at this meeting. They were just standing behind. So you can see this picture much more clearly on the internet anywhere. So on this slide, I summarize the Bohr complementarity ideas. So just main point, speaking about the trajectory of a particle has no meaning unless the experiment is designed to observe it. If the apparatus can perform the measurement of the position of the particle, it perturbs it in such a way that the wave aspect vanishes and all information about the phase of the matter wave is lost. So you have to decide if you want to see the position or the phase. If, on the other hand, the fringes are observable, the experimental apparatus cannot provide any information about the trajectory. Observing trajectories or interfering patterns are two complementary aspects of physical reality, which require different experimental procedures. And the measurement, one very important point is the measurement always perturbs the system by the amount necessary to ensure that the complementarity principle is satisfied. So here I repeat the same idea. What I want to say, it's not even necessary to measure. If you put the fringe, the moving slit in the experiment, even if nobody looks at the moving slit, you will lose the fringes because the system, there will be some information which will be leaking into the moving slit, whether you look at it or not, and then the fringes will disappear. A very important point is this principle extends to other kinds of measurements which are performed to measure complementary observable, about which you cannot have simultaneous information. And next week I will talk about spins, and it's the same. If you measure one component of a spin, you lose information about the orthogonal components, and this is something which is related to what I'm discussing today. I also conclude by something I already said. This complementarity is not an independent, this idea is not an independent principle of quantum physics. It's a consequence of the measurement postulate that I will describe in the second part of the lecture. I have spoken so far about the Heisenberg uncertainty between position and momentum. There is another one which is clear between energy and time for the same reason as I discussed before. Delta E, delta T has to be at least of the order of h bar. And what does it mean? It comes from the Fourier transform. Again, it's a mathematical property, but what does it mean physically? It means, for instance, that if a photon is created in a very short time interval, it means that delta T is very small, then delta E would be large. In other words, the energy of a photon or its frequency will be spread out if the photon has been created in a very short time. It means also that if you have a shutter that you open and close during a very short time interval, the pulse light which goes through will have a dispersion in frequency. It also means, because it's not only valid for light, that any system for which you make a measurement in a very short time will have a dispersion of energy because of that. So this is the Heisenberg uncertainty, time, energy, uncertainty relation. And again, this is something that Einstein challenged. And I want to spend 5 minutes on that because it's a very interesting problem which was raised in the Solvay meeting, not of 1927, but 4 years later, in 1931, there was another big meeting in Brussels. Einstein and Bohr came back, and Einstein thought that he had an idea to challenge this uncertainty relation. He had found a way to imagine an experiment for which you could have a very short delta E and a very small delta T at the same time, violating this rule. And this is a famous photon box thought experiment that I will try to describe here. So what Einstein said is that, and again, it's a thought experiment, even if it's not realistic, it's a matter of principle. Assume that you have a box with mirrors inside, so that if you have photons inside, they will bounce on the box, and you don't take into account the fact that they will disappear. You assume that the mirrors are perfect. And then you have a shutter. You can open on the side a small hole, and you have a clock which can time the moment in which we open the shutter and the moment where you close it. I assume it's a time as short as you want. We call T0 the very short time during which the shutter will be open, and then it closes again. And I want to measure the change of energy in the box. What do you have in the box? I have photons, but the photons have a mass equivalent to their energy according to the formula h nu equal mc squared. So the box will be heavier if there are more photons inside and lighter if there are less photons. So I will weigh the box in the gravitational field of the Earth. So the box is suspended to a spring. Here you have an arrow which points to a ruler. And depending upon the number of photons that you have in the box will be high or low. And the question is, I can take as long as I want to measure, because I can take all the time I want to measure before I have done this opening and closing of the shutter. And then I let the photons escape, so the box will go up, and I take all the time I want to measure after. So I have no, what Einstein said, they have no limit to the precision to measure the change of the equivalent mass in the box. And I have no limit about the duration of the opening, so I can violate the Heisenberg uncertainty relation. And of course, Bohr was very much agitated, and he did not know, he did not understand immediately the answer. What I want to stress is that what Einstein assumed here is special and general relativity, the equivalence h nu equal mc squared, and the fact that in a gravitational field, the mass of the photon will change in energy. So Bohr spent the night, said he spent one night sleepless, and in the morning he came back, and at the breakfast in the hotel where the conference was being staged, he gave the explanation to Einstein. He said to Einstein, "You have forgotten your own general theory of relativity. You made a mistake in the argument, and it goes here in the way that I will explain here." So, in fact, the gravitational force which is acting on the scale spring has an uncertainty delta m, because you have a small uncertainty in the mass. So you will have an uncertainty delta f equal to g delta m, where g is the acceleration of gravity. So you have this uncertainty on the force. But the force, of course, the force is acting during the very short time that the shutter is open. So this force acting during this short time produces a momentum which has an uncertainty, which is the delta f times this time, delta f t0. So you get a delta p equal to g delta m t0. But if you have a delta P, according to Heisenberg, you have a delta Z, which is H over delta P. So the uncertainty in the mass change give you an uncertainty in the position of the clock, the position of the box. But the position of the box is, of course, related to the position of the clock. And what we learned in general relativity is that if the clock changes of altitude, its rate of ticking changes by a quantity which is G delta Z over C squared. Delta T naught over T naught is G delta Z over C squared. Now, if you take these two formulas, you find H bar over delta MC squared T naught disappears, and you find delta MC squared delta T naught is equal to H bar. So you find that there is a correlated uncertainty between the uncertainty in the energy in the box delta MC squared and the uncertainty delta T naught. And so it was very humiliating for Einstein because he had forgotten his own theory of relativity. At that time, it was, of course, a thought experiment. But as I told you in the beginning, now we can measure shifts due to general relativity with a difference of altitude about 1 millimeter. So now this experiment would be, or a version of this experiment would be possible. And you see, I think it's rather strange. There are some people who challenge this explanation. They say it's not very clear to use general relativity to escape from a problem raised by quantum physics, because relativity and quantum physics are not part of a very consistent theory yet. But in fact, you have to use this argument because this is what Einstein put this argument to start. If you don't believe in the fact that mass is equivalent to energy and that mass is that photons are attracted, then you cannot do the experiment. And what the experiment is discussing is general relativity at the limit where the velocities are very small, at the limit where you have very weak gravitational field. So at this limit, classical general relativity is okay. We are not talking about black holes and about divergence of general relativity at in very unusual conditions. We are talking about the conditions that Einstein put to describe the experiment, and it's quite clear that all is consistent, and it's clear that general relativity has saved the Heisenberg uncertainty principle in this case. Another remark here, the fact that atoms have a minimum size is also related to Heisenberg uncertainty relations. You know that according to Bohr, the smallest orbit has a radius A naught, which is half an angstrom, and the electron cannot fall on the nucleus. And what Heisenberg discussed is that this is due to the uncertainty relations. Because what would happen if the electron was falling on the nucleus? The position of the electron will become more and more precise. So it means that its momentum will become more and more diffuse. So the kinetic energy would increase. And the position that the electron takes at half an angstrom from the nucleus is a compromise between not decreasing too much the potential energy at the expense of increasing the kinetic energy. And if you look at the minimum, you find exactly the Bohr radius. So the fact that the electron stays at a finite distance from the nucleus is an effect of Heisenberg uncertainty relations. And the same arguments explained also that the harmonic oscillator cannot be still, because if it were still, if it was falling at the center of the attraction, the position would be well known, but then the momentum will be spread, and you have half a quanta, which are called the 0-point fluctuations of the oscillator, which is a compromise between decreasing too much the potential energy at the expense of the kinetic energy. So why is matter occupying a large volume? It's a combination of two principles: the Heisenberg uncertainty relation, which prevents electrons from falling on nuclei, and the Pauli exclusion principle, which forces electrons to occupy larger and larger orbit because they cannot condense on a single orbit. So all of physics and chemistry is very deeply rooted into these two concepts. The last point I would like to comment upon, because it's also something very deep and very interesting, is the fact that this time energy uncertainty relation put a limit on the precision with which you can measure the phase and the amplitude of an oscillator. And I take this in the case of photons. Assume that you have a mode of the electromagnetic field in which you have a well-defined photon number. Let's say 3 photons, 5 photons, 10 photons. If the photon number is well-defined, it means that the energy NHU is well-defined. And if the energy is well-defined, it means that the phase cannot be defined, because in fact, this is a relation, the uncertainty relation between time and energy. It means that the time at which the wave arrives at a maximum is completely diffuse. And this is what I have tried to show classically. It means that if you have a well-defined photon number, in fact, you have a wave which is randomly distributed in phase. It's a well-defined frequency, but the phase is completely random. So what can you do if you want to precise the phase? You have to superimpose different photon numbers. And so you have to make a wave, you have to make a superposition of different photon numbers around an average value n bar. And the width in the photon number delta n is related to the width in phase, delta phi. You have delta n, delta phi of the order of 1. This is something which is exactly the same as C. And if you divide now by n bar, which is the average number, you have delta n over n bar, delta phi is equal to 1 over n bar. So what is the best compromise? The best compromise is when you get delta n over n bar and delta phi both equal to 1 over square root of n. Then you satisfy the condition, and you have the best compromise between having a well-defined phase and a well-defined amplitude. And this is a famous relation in optics. The average, the delta n over n bar is of the order delta phi 1 over square root of n. And this means that if you want to have a well-defined phase and a well-defined amplitude, you should have a lot of photons. You should have n bar as large as possible. And the more photon you have, the more precise you could have the amplitude and the phase. And this is very important, for example, in the device, in the gravitational wave antennas, which measure the passage of gravitational waves. There are laser beams which circulate over several kilometers distances, and you have to be able to be sensitive to 1 billionth or less than 1 billionth of an interfringe. And for that, you need a fantastically precise phase for your laser beam, which means a very large amplitude. And in fact, the laser beam which circulates between these mirrors have 100 watts of light power in order to get the kind of precision which is required to perform this measurement. So I will stop, I think, at this point. I have tried in the first part of the lecture to give you a qualitative idea about this very puzzling phenomena which Bohr and Einstein have come to, and not only them, but all the people who discuss these ideas. And in the second part of the talk, I will try to put this in a kind of formal context using the modern formalism of quantum theory. So I will resume in 10 minutes.